Hello everybody, welcome to our second video on gear design. In this video we're going to provide kind of an overview of spur gear design. So if you haven't seen the previous video which explains how you select the number of teeth and kind of gives you an overall introduction to gears, I'd actually recommend that you go back and take a look at it. Okay, so the gear design, the good thing is it actually offers you a lot of flexibility. So essentially because you're actually going to be taking that material and then having somebody machine it, you can choose a lot of things. So you can basically figure out if you want like a really thin gear or a really thick gear. You can choose the material. When I say material, it also includes kind of the heat treatment of the material to get the desired properties. You can also choose surface conditioning, like how well you want things finished and so on. So that's the good thing. And the bad thing is, as a designer, you have to provide or you have to have an idea of calculating all of these parameters. The gear design itself is two steps. So the first one is you will kind of have an idea of the RPM reduction that you want. So if you want to go from 1000 to 10 RPM, you have a reduction of a factor of 1000. So based on that, you can select the number of teeth, which is basically discussed in our previous video. The next step is you want to transmit some amount of power. So based on that, there is going to be loads that are involved. And based on the load, you would want to prevent the gear from failing. So that is the main step that you're going to be focusing now. The link over here, the UI.ie, actually provides kind of a good overview of different kinds of gears. And if you haven't seen it, you can kind of take a look at it. So that's a good link. Okay, so how do the gears themselves actually interact? So if I have this gear, this guy over here kind of rotates in one direction. So the bottom gear is going to be rotating in the opposite direction. So what that basically means is there is going to be a kind of interaction between the two gears over here, and then if you take a closer look at the two gears, basically kind of zooming in that region, you can see what actually happens. So we can kind of move these gears out and then see what are the forces that are involved. So essentially you're going to be applying, because this gear is rotating in this direction, think of this gear as actually kind of like stopped in place. This gear wants to force it to kind of rotate in this direction, right? So that basically means that this gear number 2 painted in red is going to be opposing the motion, and so it's going to be kind of like pushing against the direction of rotation. So basically in this gear, this kind of rotates this way, and this gear teeth wants to essentially move in this direction, right? So essentially this gear is forcing it to move in this direction. So this force actually opposes the direction of motion. This force basically moves along the direction of motion. So basically power is being removed here and then added here. So what you can basically do is kind of think about what are the actual values of forces that are involved here, right? So basically you can think of Wn as the normal force of interaction, and then we can basically resolve these components, right? So you can basically think of kind of resolving it along the tangential direction, which is going to be Wt, and then the same Wt appears in the bottom. So we're going to write Wt here. And then if you resolve it along the radial direction, we can write that as W sub r. And then similarly, W sub r appears on the red gear as well. So we'll write that here. So the next thing is we want to figure out how we will actually resolve this. So keep in mind that we already discussed the term about pressure angle, which basically represents this angle over here. So this is going to be the pressure angle given by phi. And then what we can basically do is kind of resolve all of our values. So if phi is the pressure angle, what we can do is write Wt in terms of Wn. So Wt is actually going to be Wn cos phi, right? And then Wr is going to be the sine component. So Wr equal to Wn sine phi. And then what we can do is we can think about what these forces are actually going to do. So Wt actually acts in this direction. So it's going to kind of cause a bending in both of these gears. So we can say Wt causes bending. And then Wr is the radial force. So that's basically going to, the Wt is going to basically cause a bending over here. And then Wr is going to cause compressive force on the two gears. So typically we are not really super concerned about the compressive stress. We are mainly concerned about the contact stress. So basically what we'll do is we'll think about design so that both stresses are basically both stresses we can say below failure. So that's the objective of our design process itself. So typically what happens in the design process itself is you'll probably know the power. So first we'll look at the formula for the tangential force based on the torque. So basically we already know that if this is my gear and the force is being applied over here, so this is Wt, and this distance is going to be kind of the radius, right, which is going to be half the diameter. So based on that, I can basically write this formula over here. So the torque is going to be the tangential force times the radius, which is half the diameter. Now the power itself is given by the torque times the RPM. This is kind of the standard formula. So using that, we can basically calculate the torque, or rather the tangential force in terms of the power, the RPM of the gear, as well as the diameter. So you have this factor 2 that comes from the diameter here. This value, because the force needs to be equal, and then you can also kind of go back and check, would be equal both for the gear and the pinion. And then so we generally drop the subscript, and then we can say for either the gear or the pinion, the tangential force would be 2 times the power divided by the ND. So typically when we have what's known as the imperial units or the British units, which is what is used in the US and unfortunately might end up using even if you're in Canada, the diameter is given in inches, the force is in pounds, the power in horsepower, rotational speed in RPM, pitch speed in feet per minute, and the torque is in pound, foot pound or pound inches. What basically happens is this becomes kind of really interesting. And then Vt is divided by 12. So this is in feet per minute. So unfortunately, it's kind of like a mixed unit. So we'll kind of give you the unit, and this is the formula that's used in the MOT book. So we'll kind of unfortunately continue to use these values. Okay, so kind of moving along. So we look at what happens, like basically use a sample problem to see how we can calculate or kind of use this value to calculate stuff. So this is our problem. So we're going to calculate the W sub T, which is the tangential, and W sub N, which is the normal force for the gear. Assuming PD, if you recall, PD is the diametral pitch, 20 teeth, transmitting 20 horsepower at 1000 RPM. So we're going to assume phi or the pressure angle is 20 degrees, which is the most commonly used pressure angle. Okay, so now actually solving this. So first let's calculate WT. So WT is going to be 12600 times P divided by N times D. So this is the formula that we had. So for this, we need to actually calculate N. So N, if you recall from before, we need to calculate D. N is actually already given to be 1000 RPM. So D, if you recall before, D is actually N over PD. So let's write that. So D is N over PD, which becomes 20 divided by 0.5, which is 40 inches. So hence we can calculate the WT, substituting back in the above formula, which gives us WT, hence WT is 63 pounds. We recall from before the equation between Wn and Wt. So basically Wt is equal to Wn cos phi, right? Because that's the cosine component. So we basically write Wn is Wt divided by cos phi. So which basically gives us 64.404 pounds. Right, not too difficult. So then let's look at what actually happens next stage. So this, if we recall, is actually going to cause bending stress, right? So let's look at what happens. So this is my teeth. My WT is going to basically be acting like so, as shown in the arrow. And so it's going to cause kind of compression on one side and then tension on the other side, which is the classic bending case. So if we think about it, we can basically say the stress we can basically calculate as Wt times some height divided by sectional modulus. So let's write that. So stress would be Wt times some height divided by the stress or the sectional modulus. So let's actually write the formula. So this basically becomes slightly interesting. So the formula that basically becomes is, because the height and the sectional modulus are going to be a function, so the sectional modulus will be a function of the width as well as the geometry, and then the height is a function of the geometry. Things get more complicated, and so we're going to write this in terms of the diametral pitch, which kind of is a measure of the height, as well as the face width, and then we'll use a geometric factor. So the formula that's given in the book is St is Wt times Pd divided by F times J. So we're not done yet. So this is kind of the nominal value, but then what we do is, since this is kind of empirical under ideal condition, so we basically multiply this by a slew of factors. So we basically multiply it by Ko, Ks, Km, Ks, Kv. So you can look at the book for more details on what these factors are, but I just have copied the figure with the table which lists what these are. So essentially J is the geometry factor. So for this you would refer to figure 915. This is from the fifth edition of the book. The K sub O is the overload factor, which kind of measures what is the shock factor. So essentially, if the loads are smooth, then there isn't as much kind of like the kind of oscillating. The maximum value is lower. The Ks is the size factor. Km is the alignment factor, which is kind of given in equation 917. For that, Cpf is the proportionality factor, and then you have the mesh alignment. The rim factor, typically if it's a solid gear, we're basically going to always assume this Kb is to be 1. This is unless there is something else going on. Kv is the dynamic factor, kind of the velocity factor. And then the equation and table for Kv are given here. Right, so this kind of gives you what we can do. So let's look at how we can actually solve or kind of use up some of the example values. So this is the figure 915. So we're going to try to calculate the J for a 20 teeth pinion mating with a 50 teeth gear. Given that this is kind of continuing from before, so given that 63 pound load is applied, PD is 0.5, calculate the stress if all the K factors are basically 1. So kind of this is fairly straightforward. Essentially what we do is, in the previous step, we're going to assume all of these factors here. We basically going to neglect this and just use this formula over here to calculate. So the only thing that's given is, we know this Wt, we know Pd, we need to calculate F, and then we need to calculate this J over here. So how do we do this? So we're basically going to look at the number of teeth. So since this has 20 teeth, so let's look at, so 20 is over here. So 20 is over here, and so we're going to basically draw a line going kind of up here, right? So this is 20 teeth. This is where everything is going to lie, and then let's look at the thing over here. So we basically find 50 teeth on the mating gear is over here, and so we're going to basically extend this line, kind of extend it all the way here, and then this is where we meet, and then we kind of draw this, and then this gives us the value for that we're going to take. So this comes out to be 0.33. So then we can use this. We already know Wt, we know Pd. So we're going to calculate F as, so the formula that we'll use is St is Wt times Pd divided by F times J. F is 12 divided by Pd, which comes to 24 inches. So substituting all these equations, so this basically gives us St is 63 times 0.5 divided by 24 times 0.33, which gives us 33.977 pounds, and sorry, pounds per inch squared. Right, so this is the stress, so you notice that the stress is like extremely small, which is because the PD that I chose is actually like really large. But this nonetheless kind of illustrates the how we would actually calculate the value of the stresses. Okay, so the next step is we're going to try to calculate all the values for K. Basically, we'll try to calculate the values of KO and KS, and the rest of it I'm going to basically let you guys kind of figure it out yourself. So for an electric motor with PD is 5, number of teeth is 20, RPM is 100, a fan driving another fan. So I'm going to basically have you calculate the value of KO and KS and then kind of extend it to calculate basically KB and KB as well. So for the electric motor driving a fan, it's a light load. So we're going to see page 337 to get kind of, this is basically coming from page 337. So what that basically means is we can basically use our table and then calculate that KO is 1.25 and then KS is 1.0. So the rest of it you can actually refer to the table and then figure out how the values come up, and then we'll kind of do it in more detail when you're actually doing the calculation. So this is fairly straightforward, so you can kind of go one table after the other and then try to look up these values. So let's look at what contact stress is. So we basically, when I said we're going to be trying to design how the gears actually, what actually happens to the gears. So when the gears are actually touching each other, we basically said there was a normal value which would kind of cause a contact stress. So let's actually examine a little closer what contact stress is. So imagine I have two surfaces, just arbitrary curvatures over here, and then if I kind of squish them, so you can think of taking the stress ball or rubber ball and then squishing them together. So what is going to happen? So I'm going to apply the load over here. So I'm going to apply two loads. So when I do this, basically the material is going to deform. So basically this kind of squishes, the bottom one also squishes. This basically assumes both of them have the same stress, so they kind of deform the same amount. If they have unequal, so the top ball, if it's softer, that will deform more, the bottom ball might deform less. So what we basically see is that the object, we can assume that the objects are actually initially in point contact. So this is the stress that would potentially develop. So we can basically think about this being initially the objects have a point contact. So as the force is increased, more area comes into contact. So this basically means that the stress is a function of the load, because if the load is 0, there's not going to be any stress, as well as the geometry, as well as the post-elastic model. So let's write that down. Function of load, geometry, and kind of both elastic modulus or elastic modeling. So what this basically means is that the actual stress that we calculate is going to be slightly more complicated, and so there is not like a straightforward formula that we use, or rather there is, you could potentially calculate that, but because there is going to be the several factors involved, we're basically going to use the formula which is given in the book, which is going to be a function of the force and so on. So essentially the formula that's given is the contact stress is given by Cp. The Cp here is kind of measures kind of the effective modulus when two materials are in contact. So Wt is the tangential force. The I basically takes care of converting it from the tangential to the radial force, And then these are the same overload factor that we encountered when we're calculating the bending value. In this case, this is dependent on the face as well as the diameter of the pinion. So for CP, we can basically refer to table 910, but then when it's two steel gears are in contact, the equation, the number that you use is 2300. Notice a unit, this is actually pounds per square inch, the whole point to the 0.5, because this one is also PSI to the 0.5. Right? So the geometry factor I, for that we will basically refer to figure 921. So how do we actually design the whole thing? So that is where things get even more interesting. So basically, what we actually want to do is ensure that we can calculate and both the contact stress and the bending is lower than some failure stress. So in gears, you kind of using all the material and kind of putting all the correction factors, we kind of call these as allowable bending stress numbers for tension or bending, which is S sub AT, and then allowable stress number for contact, which is given by S sub AC. What we'll actually do is, as before, if you recall the discussion on endurance, we basically multiply this. So we're going to use some factors that are relating to the endurance limit, which is going to show up here. So that is going to be the factor yn. And then we also have the service factor that we typically like, as well as the reliability factor. Safety factor. So because of the fact that we already incorporated a lot of, made it super safe, for gear design, you're going to use a typical safety factor. So the typical safety factor that we use the typical safety factor that we use is basically 1.5, and then the reliability factor we can basically use KR as 1 because we've already incorporated the cycling effect into this calculation. So for gear, previously we recall the other design, so you kind of somehow choose the material, maybe like what is cheap or kind of what you think might be acceptable, and then kind of calculate the diameter of the material. So if you imagine you're designing a table, so you basically say, okay, I'm going to use mild steel. I know the Young's modulus and the yield strength, and so based on that, I'm going to adjust the diameter of the legs or so on. The gear, it kind of is slightly more different. What we typically do is we choose the diametral pitch, which gives us a recommended face value. So based on that, we can calculate, based on the power and so on, we can calculate what are the stresses that are going to be involved. And then based on that, we kind of say, okay, you know what? I need to make sure that the material can handle, say, 100 psi of bending stress and 200 psi of contact stress. And then based on that, we're going to look up the material. So these would be the typical design stress steps. So first one, what we do is from the design requirements, we're going to identify the input and output speed, the power transfer required. So based on that, since we're going to use a 20 degree, sorry, this should be 20. So the happens is from the design requirements, we identify the input speed, the output speed, power requirement. So typically we use a gear with a 20 degree pressure angle, and for this the minimum number of teeth is 70. So the actual number of teeth calculation is kind of independent. So we'll basically say determine the number of teeth, which is basically from the previous video. So we also want to ensure that it's less than 150 teeth. If we can't do that, we basically use like 2-stage gears. So for that, refer to the previous video. Next, what we do is we pick an AGMA number from table 9.3. So this is based on the application. So if you want to use it for a gyroscope, you typically need a very accurate gear. If it's a not so great application like a cement mixer, you have a lower grade or lower quality gear that you can get around. So typically the finer the gear, the more expensive it becomes. So you want to choose the lowest number that's acceptable. So after that, we're going to pick kind of the class of material. So are we going to do like steel, cast iron, or bronze? So steel is usually preferred because it gives you a lot of versatility in a calculation. You can do heat treatment and so on. So you can also do the bronze gear, but then all of the problems that we'll be dealing with is going to be basically assuming it's a steel gear. The next thing is we find the overload factor. So this is determined by the input and the output characteristics. So if you have like an electric motor driving a fan, the load is going to be very small, or the overload is going to be very small. If it's going to be kind of an impact case, then we need to use a higher value. Then we specify a trial pitch. For this, we use figure 9.27, 9.24 in the new book, and then 9.27 in version 4. This provides an initial guidance. And then what we do is we already calculated the overload factor over here. And then from that, we'll basically calculate the desired power as KO times the power. Because a number of variables involved, the PD that we actually get from the figure 924 is actually kind of the initial trial. So you might have to kind of go back to get a more or a better quality or a better design. Then we'll calculate the phase width, which is basically a recommended value of between 8 divided by PD to 16 divided by PD. So we pick the one in the middle as the recommended average value, which is 12 divided by PD. Then we specify all the other parameters in terms of if it's going to be enclosed gear, outside gear, if it's going to be like multi-step, and so on and so forth. And then once we do that, we kind of proceed to actually computing the stresses. So to compute the bending stress, this is typically the contact stress of the pinion is a limiting factor. For this, we basically need the value of NC, which is the number of cycles for which you want the gear to last. So given the lifetime in hours, the speed in RPM, Q is the number of times the gear gets loaded per cycle. The equation is NC is 60 times L and Q. So the 60 basically comes because of our conversion from lifetime being in hours to the RPM being in minutes. Then we'll calculate ST prime, which is kind of a corrected value, or this is basically the design or the required or the desired value for our stress that for the material property of the material that we will select. So this is basically from the previous equations, we just like jumbled them around. So this is basically in terms of the safety factor, which if you recall typically is about less than 1.5, but typically we can use this value to be about 1 under specified. Similarly, KR, we can use this to be also 1 unless otherwise specified. And then the YN and ZN basically comes from our table. So you can basically use this to calculate the ST prime and SC prime. So once you have these two numbers, what we'll typically do is we'll kind of look for a material that satisfies these properties. So if it's a bronze gear, we'd refer to table 9.6. For steel gears, ST prime and SC prime, we're going to check figures 9.11, 9.12 for through harden. And then if it's not possible, we'll either need to choose a lower value of PD. So keep in mind that if you choose a lower value of PD, your gear becomes stronger or bigger. Otherwise, we can basically look at case hardening and other things. So once you get a hardness number, this is only for steel. Once you get a hardness number, you can refer to the appendix 3 and 4, and then you can kind of get an idea of what material that you list. And in the book, table 9.4 lists the typical material you use. You can kind of iterate this again and again. So the book kind of refer to that section, so it tells you how you iterate, what are the conditions that would be needed. If you're designing a plastic gear, the procedure itself is reasonably straightforward, but with plastic gears, you need to keep the shrinkage and other parameters in mind. So you can look at the example 9.7 in the book, which gives you details here. So this basically, so once we do that, we would kind of have the final gear, and then we can basically say, okay, you know what, this is the gear size I want, this is the diametral pitch. The person actually manufacturing, so you can look up the videos on gear manufacturing, would basically either hob or cut the gear to our required specification. So this concludes our introduction to gear. In the next video, we'll look at actually solving an example using the like kind of a sample problem, and then we'll be referring to Machine Elements in Mechanical Design, 5th edition by Robert Mott. Thank you.